Okay, so till now we understood the thermodynamics of pure liquids, pure gases, or what we can refer it as thermodynamics of single component systems. Now, if we have multiple components, then what type of thermodynamic framework do we adapt to? And the first and the most important quantity that comes into picture is partial molar property. So, for mixtures, whenever you have multiple components, you will define quantity called partial molar property, and partial molar property is defined as any property that is denoted as Bi bar and is defined as del B by del Ni at constant T, P, Ni star. And if you remember our notation, Ni star means all the Ni's except this I. Okay, and this partial molar property can be any extensive property. It can be internal energy, it can be entropy, it can be enthalpy, it can be Gibbs free energy, any property of extensive property of the system. But this is defined with respect to the ith component. This is defined with respect to the ith component. So if you have n components in your system, then you will have n number of partial molar properties. Okay, and different partial molar properties defined with respect to different components will obviously be different. But if you want to find out the relationship between Bi bar, which is the partial molar property defined with respect to ith component, and B, the bulk property, observed property for the mixture. So what is the relationship between these two? So for this, what we do is we resort to our original definition of and the first postulate following which I can define B as a property defined in terms of two independently variable properties, and let me say those two properties are T and P, and N1, N2, and N capital and so on. Okay. And therefore what can I do is I can write dB equals del B by del T at constant P, N1, and capital N dt plus del B by del P at constant T, N1, and capital N dt, plus for the derivatives with respect to Ni's, I can write summation I going from 1 to capital N del B by del Ni at constant T, P, Ni star dNi. And what I observe is that this particular quantity is nothing but my partial molar property. So therefore I can write dB equals del B by del T at constant T at constant P, N1, and capital N dt plus del B by del P at constant T, N1, and capital N dP plus summation for n component system going from I equals 1 to n, and I have here Bi bar dNi, where Bi bar is my partial molar property. Okay, therefore I have now the relationship between dB and Bi bars. Okay, now what I can do is I can do an Euler's integration to find the relationship between B and Bi bars. Okay, and my original expression was B as a function of T, P, N1, and capital N. And if I remember my Euler's integration, is simply f equals x del f by del x plus y del f by del y, and this will be for a thermodynamic property, and in general I have h times of f, where h is the order of dependence. So now I know that order of dependence on t and p are all 0 and ni is all 1. Therefore I can write b as simply summation that goes from 1 to capital N bi bar, because bi bar is the derivative, times Ni. So that is how my bulk property, a property of the mixture, depends upon the partial molar property of the system. Okay. So now I can always write down a generalized Gibbs-Duhem equation. So remember our Gibbs-Duhem equation at constant t and p was nothing but summation I equals 1 to capital N Ni d mu I equals 0 at constant t and p. Okay, and if we observe mu I and its definition defined with respect to G, then you will find that mu I is nothing but the partial molar Gibbs free energy Dni at constant t p Ni star. So therefore mu I is nothing but Gi bar, partial molar Gibbs free energy. Okay, and if you remember how did we actually derive the Gibbs-Duhem equation, you will find that we defined G, okay, as G of T, P, N1 and so on. From here we got dG as minus of SDT plus VDP plus summation I equals 1 to capital N. Now I can write it as Gi bar times Ni. Okay, and when I expanded this expression G equals summation Gi bar times Ni. We used to use mu I, but now we know that mu I is nothing but Gi bar. By comparing these again to summation I equals 1 to capital N, I equals 1 to capital N, Ni d Gi bar plus Gi bar dni. By comparing equations 1 and equation 2, what I get is simply summation Ni d mu I equals 0, which is again nothing but summation Ni G d Gi bar equals 0. So in a similar manner I can write the generalized Gibbs-Duhem equation. So generalized Gibbs-Duhem equation, and what would that be? Generalized Gibbs-Duhem equation would be simply del B for any property, del B by del T at constant P N1 and capital N dt plus del B by del P at constant T N1 and capital N dP plus minus summation of Ni d Bi bar equals 0, and from this at constant T and P we can write that summation Ni dBi equals 0. So this is a generalized Gibbs-Duhem equation. So Gibbs-Duhem equation can always be generalized to to represent any partial molar property, and the chemical potential itself is a partial molar property, specifically the partial molar Gibbs free energy. So now if we be specific, and suppose I want to know the partial molar internal energy. Okay, so I denote for it as ui bar, and this will be defined as del u by del ni at constant Tp ni star, and it is to be noted that this is not equal to mu I. This is not equal to mu I, because our definition of mu I was when defined with respect to u, it was del u by del ni at constant S, V, and I star. Okay, so you must remember that these quantities SV and these quantities Tp are different. Therefore, you have ui bar not equal to mu I, but del u by del ni at constant Tp and I star. Now what do I do is I define similar quantity called partial molar enthalpy, and I denote it as Hi bar. But if I want to define it in relation to a partial molar internal energy, then what is this? What is this in as a function of ui bar? Okay, so I know that H equals U plus PV. Okay, so what I can do is I can differentiate both the sides with respect to Ni at constant Tp Ni star. I can do this both the sides. So what I get is del by del Ni at constant U plus of U plus PV at constant T Pni star. Okay, and what we then get is Hi bar equals del U by del Ni at constant Tp Ni star plus, now del by del Ni of PV, but here we have P as constant, so I can write this P times del V by del Ni at constant T P Ni star, and what I observe is that Hi bar is this quantity is nothing but ui bar plus P times Vi bar. Okay, and if I write my original equation, I have H equals U plus PV. So what I observe is that I convert all my extensive variables simply to partial molar variables, and that's how I get the relationship between Hi and Ui, and therefore I can write Ai, again I can write Ai as Ui bar minus Si bar times T. I can write Gi bar as Hi bar minus T times Si. So I have an entire thermodynamic framework which can be defined with reference to the partial molar quantities. But suppose I am interested in finding the variation dGi bar. How do I do that? I want to know dGi bar. So I again resort to the original method, that I have dG, and this is equal to minus SDT plus PdV plus summation I equals 1 to capital N mu I dni. This is my original definition, and there now I use del by del ni operator on both the sides. Okay, and then since differential operators can be exchanged, I simply get d of gi bar. But then when I operate this, so okay, let me write this del by del ni of minus of s dt. Okay, and this has to be done at constant t p ni star. Okay, plus and so on. So when I do this, I have to operate this once on s keeping dt constant, and once on dt and keeping s constant, and therefore when my t is constant, I simply get rid of this dt term. So what I get is an expression which is as simple as this: dgi bar equals simply minus si bar dt plus, okay, so here in this particular place we need to have a correction. This has to be plus vdp. Okay, and therefore when I operate this on vdp, I get vi bar times dp plus. Now when I have to operate this operation has to be done very carefully. I have to go from 1 to capital N, and I have del by del ni times mu I dni, mu times mu I dni at constant t p ni star. And now, so these two terms are fine. So first term is okay, second term is okay. But when I have to do a differential here, then I have to be careful. And what I get on differentiation is a quantity like this. So my original quantity is this. So let me write this quantity. This is my original quantity, and this is equal to, I have to first operate this differential operator on mu I, so that will simply become summation. Now I need to choose another index j which goes from 1 to capital N. Okay, and this will become del mu I del mu j by del ni, and I keep this t p ni star as constant, and times dni plus. Now I do a differential on the second term, keeping mu I as constant. I get del d of del by del ni of nj. This quantity is interesting. I have d of del nj by del ni. And what is this quantity equal to? This quantity says that the variation of jth component is traced with the variation of the ith component, and this happens to be equal to what's we called as the Kronecker delta. So Ni and J are independent. So therefore, if you vary the number of moles of ith component, the jth component is not going to vary. So therefore, when I is equal to J, and that means I get a condition of d of del Ni of by del Ni, which is equal to 1, and this is equal to d of 1, and this is equal to 0. Okay, and when I is not equal to j, okay, so d of del n j by del ni so this is d of 0 because I and j do not depend upon each other, and therefore it will be 0. So let me make a correction here. This particular term is the Kronecker delta, and therefore I have this as d of the Kronecker delta function. Okay, so therefore in this particular expression, this term will become 0. Okay, this term will become 0, and therefore what I get finally is simply dgi bar equals minus si bar dt plus vi bar dp plus summation j going from 1 to capital N, then the derivative of the potential of the chemical potential times dni. Okay, so this is how the partial molar Gibbs free energy vary, and its dependence on Tp and Ni. Okay, so now therefore what we understood from this particular concept is that whenever you have a quantity which is there in your thermodynamic framework for pure components, you have an equivalent quantity when you have to define a mixture. Okay, the mixture can be gaseous mixture, it can be a liquid mixture. So you have a volume, and if you have to define that with reference to a mixture, then you have partial molar volume and so on. So now what we will do is we'll try to understand the thermodynamics of different mixtures, and this can be done either using PBTN relationships, or it can be done more easily using the concept of partial molar properties, or in other words we can say that this can be defined in an easier manner if you use the chemical, what we call as the chemical potential framework. Okay, so now we have new definitions. Okay, so for let's say I have an ideal gas, and what do I define something as an ideal gas? I define a gas to be ideal if it follows the equation mu equals mu I0 plus RT ln P. Okay, so if the gas follows this equation, mu equals mu 0 plus RT ln P, then I define the gas to be an ideal gas. Okay, we will see in detail why do we do this, but for now I use this as the definition of an ideal gas. Now if you have an ideal gas mixture, again we are going to go into the details why we have mu 0, what are the characteristics of mu 0 and so on. But if you have if you want to define something called an ideal gas, it has to be a gas which follows mu equals mu 0 plus RT ln P. If you have ideal gas mixture, then you have a quantity called mu I, because you have to now define the chemical potential with reference to every component, and this will be equal to mu I0 plus RT. P in this previous equation is the total pressure, and here this will be replaced by ln Pi, which is the partial pressure. And if you have an ideal solution which is a liquid mixture, then you define it as mu I equals mu I asterisk plus RT ln Xi, where Xi is the mole fraction. But now let me give all the conditions under which you can use this framework. Okay, so this is important that mu I or mu I naught in these equations are functions of temperature only. Okay, so if this framework has to be made applicable, you must keep mu I or mu I naught as a function of temperature only. Okay, and P in the first equation is the total pressure, and Pi is the partial pressure. Okay, is the partial pressure. And what is the relationship between total pressure and partial pressure? If Yi is the mole fraction of the ith component in the gas, then Pi equals Yi times P. Okay, Yi times P. This is another condition. Xi is the mole fraction again of the ith component, but this is in liquid. This will be our general notation, and this is in gas. Yi would be used for gas and Xi for liquid. And finally, mu I asterisk is a function of both temperature as well as pressure. We don't say that it is a function of temperature only. So this is our framework to define an ideal gas mixture, and an ideal solution, a framework utilizing chemical potentials. So when I give this mu equals mu naught plus RT ln capital P as my definition of an ideal gas, so is there any way for me to confirm it? Therefore I manipulate this equation and try to see if I reach the same ideal gas equation which I know is something which we have been using for defining an ideal gas. So what I do is I differentiate both the sides with respect to P. So I have with respect to P, I have mu at del mu by del P at constant temperature and N1, N2 and so on equals del mu naught by del P at constant T, N1 and so on plus RT del by del P of ln P at constant T, N1 and so on. But what about this quantity? This quantity simply is 0, because we have defined mu naught as a function of temperature only, and if you keep the temperature constant, this quantity must become 0. Therefore I have del mu by del P at constant T, N1 and capital N simply equal to RT by P. Does this look similar? Yes, this looks similar, because in the equation PV equals nRT, you have a term which can be rearranged, and I can get V by N as RT by P. So now I need to confirm, I need to find out what is the value of this, what is this equal to. Okay, so let me see if this is equal to V by N. Indeed, because I have dg, a simple rearrangement will show this, dg equals minus sdt plus vdp plus summation mu I dni. Okay, and what do I do? I can simply use this expression and get this as del G by del P at constant T, N1 and capital N equals V. Okay, this is equal to V. But for a pure liquid mixture, for a pure liquid, what you have is G is simply mu times n, Therefore, this will be nothing but del mu by del p at constant t n1 n capital N will be nothing but v upon n, and therefore this is nothing but this is equal to v by n, which means Pv equals nRT, which is same as what we have been knowing all along, right? So therefore I can say that this framework, the chemical potential framework, actually is correct. Okay, therefore whenever we have to use the ideal gas description, we will use simply mu equals mu naught plus RT ln P. Now let's see another important feature of this equation. Let's say del mu by del T in this time at constant P n1 and so on. This will become del mu naught. In fact, mu naught is a function of T only, so therefore it will be d mu by dt plus we have RT ln P, and we should have del by del T of this quantity at constant T, at constant P n1 and so on, and capital N. Okay, so what information do we get from here? And what we get is that okay, and I can always simplify this as this quantity being simply equal to R ln P. Okay, so and what is this quantity equal to? What is this equal to? So what we can do is we can again use the same definition as dg equals minus s dt plus v dp plus summation mu I dni, and using this same procedure as before, by del T at constant P n1 so on, this will be minus S, from which I get del mu by del T at constant P n1 and capital N, as which has to be minus S upon N. Okay, negative of molar entropy. So I can use this information to find out the enthalpy of my ideal gas, enthalpy of my system. So I have the relationship between S in terms of H in terms of different quantities as G minus Ts, and I can write this as molar entropy equals mu minus T times molar entropy. Okay, and I have the expression for the molar entropy actually ready with me. So there, and I know mu as mu naught plus RT ln P. So therefore I can write H as mu naught plus RT ln P plus T times, now I will use the expression for molar entropy as minus of d mu naught by dt minus R ln P, and this on simplification becomes H equals mu naught minus T times d mu naught by dt, v mu naught by dt. So what's interesting in this final expression, what I find is that mu naught is a function of t only. Okay, so therefore when I look at this entire term, what I find is for an ideal gas, H is a function of temperature only, and this is again known. So therefore what we can say is that our thermodynamic framework in terms of chemical potential actually works. Okay, so for an ideal gas, I have mu equals mu naught plus RT ln P, as my definition, and we have proved this to be working. But what if the gas is non-ideal? So I have non-ideal gas. Okay, and you remember we started with, for an ideal gas, the equation as simple as PV equals nRT, and then we derived the cubic equations of state, and people even now are trying to come up with better and better equations of state, and the procedure is really complex. And therefore if I have to develop this, I have to use this framework, and I have to convert this P into non-ideal P, then your framework will become very complex. Okay, and therefore I want something simpler, and for that I propose the concept of fugacity, and I keep the form of the equation same, mu equals mu naught plus RT, and now instead of P I propose a quantity known as F, where F is the fugacity of the gas. Okay, and why have I proposed this quantity fugacity? So that the form of equations here and here remain similar. Okay, so I simply need to know, so for an ideal gas I simply need to know the pressure, whereas in case of a non-ideal gas what I need to do is simply know the quantity called fugacity, and in the same expression mu equals mu naught plus RT ln P, instead of P I need to substitute F. But what happens when the pressure becomes really low? When the pressure becomes really low, the gas starts behaving ideally. Therefore I have the definition of fugacity as F over P tending to 1 in the limit P tends to 0. As P tends to 0, F by P tends to 1, or the fugacity actually becomes equal to the pressure. But the question is that I must know fugacity in order to use this framework, and for that let me quickly tell you how to determine fugacity. So how to determine fugacity. Okay, and for this I follow a very straightforward procedure in which I have just now proved this, that del mu by del P at constant T and N is nothing but V over N. Okay, so therefore what I do is I use d mu at constant T and N equals V by N dP, and this has to be done at constant T and N. Okay, so let me eliminate T and N now onwards. It's understood that it has to be done at constant temperature and pressure. So I have the definition of mu being mu naught plus RT ln F. Okay, and I know that mu naught is a function of temperature only, so therefore at constant temperature d mu naught will become equal to 0. So therefore what I can write is d mu at constant T is simply RT d ln f at constant T and n, and let me eliminate this notation onwards. So therefore what I have is RT d ln f, RT d ln f is simply equal to V by n d of P. V by n d of P. Now I do a small mathematical trick. I subtract both the sides by ln of P. Okay, so what I do is RT d ln f minus RT d ln P equals V by n dP minus RT ln P, or rather d ln P. Okay, so what I now get is RT of d of ln f over P. Okay, and this is equal to V by n minus RT over P times dP. Okay, so now I can do a rearrangement, and what I get is d of ln f over P equals V by nRT minus 1 over P times dP. Okay, and I can do an integration both the sides. So what I get is integrating from 0 to P, d of ln f over P equals integration from 0 to P V over nRT minus 1 over P times dP, and I can use this process to evaluate my fugacity, but we find a quantity here f by P. Okay, this is f over P. Okay, this quantity is called fugacity coefficient. What is the importance of fugacity coefficient? This fugacity coefficient gives us the deviation of the gas from the ideal behavior. Remember, as P tends to 0, f by P tends to 1, that means the fugacity starts becoming equal to the pressure of the gas. So therefore f by P which is called the fugacity coefficient, will tell us about the deviation of the gas from the ideal behavior. Okay, and now we have here mu equals mu naught plus RT ln P, and this is for an ideal gas. And now we define mu equals mu naught plus RT ln F, and this is for a non-ideal gas. So moving further, we had mu I equals mu I naught plus RT ln Pi, and this was for an ideal gas mixture. Then in an analogous manner we can define mu I equals mu I naught plus RT ln Fi, RT ln Fi, where Fi, so this is defined for a non-ideal gas mixture, and we have Pi by Fi tending to 1 in the limit capital P tending to 0. Remember, not in the limit Pi tending to 0, but in the limit capital P, total pressure tending to 0. The fugacity of ith component Fi tends to become equal to the partial pressure of ith component. Now coming to the liquid solutions, we had mu I equals mu I asterisk plus RT ln Xi, where Xi was the mole fraction. This is defined for an ideal solution. And now we had Pi, so we had F by P as the fugacity coefficient, Fi by Pi as the fugacity coefficient of ith component. In a similar manner, we define gamma I equals Ai by Xi, where Ai is the activity of ith component, gamma is called the activity coefficient. So therefore, for a non-ideal solution, we define mu I equals mu I asterisk plus RT ln Ai, where Ai is the activity of ith component, and this is for a non-ideal solution. This is for a non-ideal solution. So we have defined something called an ideal gas mixture. Let us have a detailed look into how do these gas mixtures behave. So our working definition was that an ideal gas mixture is one which follows the equation mu I equals mu I 0 plus RT ln Pi, where Pi is the partial pressure, and we had defined Pi to be Yi times P, where Yi is the mole fraction. We are using Yi instead of Xi because we refer to Yi's when we use gas. In liquid mixtures, we would use Xi for the mole fraction. So I can write this as mu I equals mu I 0 plus RT ln Yi plus RT ln P. I have used the definition Pi equals Yi times P. So what I do now is differentiate both the sides with respect to pressure at constant T, N1 and so on. Now when I keep T constant, the derivative of this term is going to be 0 because mu I naught is a function of temperature only. But at the same time, Yi is not going to change because I am keeping N1, N2 and so on constant. Therefore, this derivative will also become 0, and I will simply have this quantity as RT over P. Okay, so del mu I by del P at constant T, N1 and so on equals RT by P. Now I want to know what is this quantity equal to. Okay, what is this equal to? For that, what I do is I start with the definition of chemical potential, and mu I equals del G by del Ni at constant Tp and I star, and from here now I differentiate with respect to pressure at constant T and 1 and capital N equals del by del P of del G by del Ni When I do this differentiation, I keep T, P, and I star constant, and for this I have T and 1 and then capital N is constant. And then I use Maxwell reciprocity relationship, from where I get del mu I by del P at constant T and 1. Now this can be written as del by del Ni, okay, at constant T, P, and I star, and I can write this as del G by del P at constant T and 1, and so on. But this term, this is nothing but volume, okay. So therefore what I get is this, so this simply becomes del mu I by del P at constant T and 1 capital N is simply del V by del Ni at constant T, P, and I star, and this is nothing but equal to the partial molar volume. Therefore this quantity is equal to partial molar volume, by which you will get P VI bar equals RT. And compare this to the ideal gas equation, PV equals RT, where V is the molar volume for of a pure component. So from this we can say that the ideal gas mixture seems to follow the ideal gas equation. But let us consider this. So we have VI bar equals RT by P, okay. And now it's difficult for me to observe the partial molar volume, so I want to write this in terms of the total volume, and the relationship between total volume and the individual the partial molar volumes is given by simply summation Ni Vi bar. So what I do is I substitute the equation above here, as now RT by P actually is independent of any of the i's. I can write this as an I. So what I get is Vi, so I can write this as PV upon Vp upon RT equals summation of equals capital N and I, and this is nothing but the total number of moles of individual components. So from where I can write PV equals an RT, and this is nothing but the ideal gas equation, right? So therefore an ideal gas mixture does follow the ideal gas equation, but an information that we get further from here is that we consider the individual volumes, and the total volume of the gas mixture simply came out to be the observed volume. That is the total volume is the sum of the individual volumes. What does this mean? This means that let me have 2 liters of oxygen, assuming oxygen to be an ideal gas, and if I have 4 liters of nitrogen, again nitrogen being an ideal gas, and if I mix them to get N2 plus O2 mixture, then what I would observe is that the total volume of this, under the same conditions of temperature and pressure, would be equal to 6 liters, the summation of 2 plus 4. So an ideal gas mixture has I can say a delta V mixing as 0 delta V of mixing, so that there is no change in the volume of the total gas after you mix the individual components. That is what happens to the volume. But what about the enthalpy of the system? So for determining the enthalpy of mixing for an ideal gas, let us start with our original formulation, mu I equals mu I naught plus RT ln. I will write directly Yi plus RT ln P, and this time I will differentiate this with respect to temperature at constant pressure N1 and capital N, and therefore what's going to happen is that the derivative of this quantity is going to 0, the derivative of this quantity is going to 0, as we have N1, N2 to N capital and P as constant. Okay, so the derivative will become 0, del by this quantity, del by del t by del t of this quantity and del by del t of this quantity. Okay, so therefore this and mu I naught is a function of temperature only, so therefore I have d mu I naught by dt. Okay, of course, but I need to make one change. I need to divide, so this is a correction here. I need to divide the entire quantity by temperature. So therefore I must make a correction here. Mu I naught by T equals mu I naught by T. This quantity is going to be, these are the quantities which are going to be equal. Then only I have independence from temperature. Okay, so then what I do is I try to find out the enthalpy of the system. Okay, and for that I start with my definition of mu I, which is equal to del G by del Ni at constant T P Ni star, and then what I do is I try to do this mu I by del T at constant P and 1 and so on, and when I operate this on del by del T of del G by del Ni at T P Ni star at constant P and 1 and so on, and then I use Maxwell's reciprocity and I exchange these two, it will turn out that this quantity del mu I by del T at P and 1 and capital N equals, this is equal to minus of partial molar entropy. This is negative of partial molar entropy. Okay, and I use this in this particular expression. I have Gi bar equals Hi bar minus Tsi bar, but this is nothing but mu I. Gi bar is nothing but mu I, so this is equal to Hi bar minus Tsi bar. Now I substitute the expression for Si bar, and what I get is mu I equals Hi bar minus T. Instead of T, I write del mu I by del T at constant P and 1 and capital N, so on. I do a mathematical trick. I divide this by T squared, by which from which I get T squared minus 1 over T del mu I by del T at constant P and 1 and n capital N. Okay, so now I have the partial expression for partial molar enthalpy of the system by T squared. I do a rearrangement, and what I get from here is simply minus H by T squared is nothing but negative, Hi bar by T squared is negative of del by del T of mu I by T at constant P and 1 and so on. And if you remember, we actually obtained this as minus of d mu I naught by dt. Okay, so therefore what do we observe from here? What we observe from here is that Hi bar is nothing but T squared negative mu I 0 by dt, from which we observe that Hi bar is a function of T only, that. And what do I understand by this? I have a binary mixture of A and B, and if I have a mixture and I am somewhere in between, Hi bar which is defined by as del H by del Ni at constant T, P, Ni star. Okay, so this means that if I add some amount of A to this system, how much is the enthalpy going to change? And if I add some amount of B to this, how much enthalpy is going to change? But this quantity is independent of composition. See, this is not a function of composition. It's not a function of composition. It's a function of temperature only. So doesn't matter where I am along this line, the enthalpy is going to remain the same, by which I can say that I add some amount of A or some amount of B to my system, the enthalpy is not going to change. So therefore delta H mixing for an ideal gas is 0. So delta H mixing for an ideal gas is 0. Now we can find this same variation for the Gibbs free energy. How does the Gibbs free energy change? Okay, so for a Gibbs free energy for this mixture, Gibbs free energy for this mixture is simply given as the summation I equals 1 to capital N, the number of components that you have, times so summation of Ni mu i's. Okay, and I can use our original formulation, I equals 1 to capital N and I, and here I will use an I0 plus RT ln Pi, where Pi is the, let me write this, Pi is the partial pressure of ith component in the mixture. Okay, and I can further simplify this as simply I equals 1 to capital N and I mu I 0 plus summation I equals 1 to capital N RT Ni ln Pi. So this is going to be the total Gibbs free energy of the mixture. But before mixing, the total Gibbs free energy will simply be the sum of individual Gibbs free energies. So therefore Gibbs free energy total before mixing, okay, will simply be Gibbs free energy of the first component, the second component, and so on till the nth component. So this will simply be again I equals 1 to capital N Ni mu I 0 plus summation. Now before mixing there is no partial pressure, but every gas is present as a pure component. So therefore I will write this as N summation RT Ni ln Pi. Now this is capital P. Okay, this is capital P, and Pi is the pressure of pure gas before mixing. Okay, so this is capital Pi, and therefore delta G mixing is simply the difference between the two, and this is equal to RT summation I equals 1 to capital N RT summation I equals 1 to capital N Ni ln small pi by capital Pi. Remember that these two Pi's are different. So this is what's going to happen. The total Gibbs free energy of mixing is going to be equal to this. Okay, and now I can use this expression delta G equals delta H minus T delta S, and for mixing I can use the subscripts mixing, and for an ideal gas mixture delta H mixing, we have proved this to be equal to 0. So therefore delta G mixing is simply minus of T delta S mixing, and therefore the entropy change on mixing is simply minus of R. From the previous expression you can write minus of R times Ni ln Pi upon capital Pi. This is the partial pressure, this is the total pressure. This is the entropy change of mixing. Now consider an ideal gas mixture of oxygen such that the initial pressure, the pure component oxygen pressure was 2 bar, and you have nitrogen whose initial pressure, pure component pressure, is 3 bar. So this is equal to capital P1, this is equal to small p2, and after mixing they are mixed in such a way that the so you have N2 plus O2 mixture, and partial pressure of oxygen becomes 2 bar and partial pressure of nitrogen becomes 3 bar. So when you substitute this in this expression or the expression for the Gibbs free energy, what you will get is delta G mixing is equal to delta S mixing, and this is equal to 0. So what do we understand by this? So what all can we write for an ideal gas mixture? The ideal gas mixtures are the ones for which the heat change of mixing is 0 and the volume change of mixing is 0. And this happens because there are no interactions which are present in the system. So since there are no interactions, the replacement of one particular molecule by another molecule is not going to make any difference in the volume occupied by that particular molecule, or it's not going to make any difference in the positions which they occupy. The molecules are not going to go farther apart, or they are not going to come closer than their original condition. Therefore, the volume which the mixture occupies is going to continue, and therefore the volume change of mixing is 0. Similarly, enthalpy appears as the energy which is required to pull the molecules apart, and since there are no interactions, this quantity is not going to change. But when you want to trace the change in in Gibbs free energy of mixing and entropy of mixing, we found that if the resultant mixture has the same partial pressure as the initial total pressures of the pure component, if that is the condition, then the mixture will exhibit 0 Gibbs free energy of mixing and 0 enthalpy of mixing.